This lecture is a continuation of the walkthrough for exercise Hurricane Part 3, looking at relationships. So in the previous video, we were looking at the relationship between death and damages from tropical cyclones in the North Atlantic. And so we took that data and we initially looked at a scatter plot of the two data sets of deaths and damages just as they were. And we don't see any relationship or any apparent relationship here. But when we took the logged values of deaths and damages, we see a much clearer linear relationship. We see this cloud of points that are clearly trending from the lower left to the upper right. And when we add the trend line, it reflects that. And so that tells us that there is a statistical relationship between those two sets of values. And it's positive from what we can tell, both by the slope of the trend line, but also visually we can look at the way it rises from left to right. When we look at the relationships between variables, there's a variety of ways of doing that. Looking at one visually, again, is a scatter plot. The trend line, which is essentially a regression line, tells us that as well. Another way, a more common way, is to look for a statistic called a correlation. And so a correlation is a way of measuring the strength of that association between those two sets of numbers. It's different from an R-square value because the R-square value is a specific setup of the data in which you're trying to predict one based on the other, which is a little bit different both theoretically and mathematically. But for all intents and purposes, a correlation is different because it's kind of agnostic in terms of what causes what or what predicts what. Rather just simply says how much do these things vary together. So if we go back to our original data set, we're going to add a statistic for that. So in order to calculate the correlation, we're going to need a number. We're going to need to know the number of cases. Well, let me back up. The correlation itself is very simple in Excel. So if we look at the correlation of logged death and logged damages, it's very simple in Excel. We take a formula that starts out with correl, short for correlation, and what it needs are two sets of numbers. It needs in this case, we're using the log deaths and the log damages. So that is, the deaths are in the range G2 to G121. Is that right? Sure. Yes. Okay. And the second set of numbers is in the J column. That's J2 to J121. Okay. And so those two numbers, those two arrays, are what we need. So it's going to look to see how much they vary together. So we just hit enter. And what we end up with a single number, a single statistic that summarizes the level of correlation. The value that you can get for a correlation ranges between -1 and +1. 0 would mean there's no relationship. -1 would mean that there's a perfect inverse relationship, meaning one goes up, the other one goes down in a perfect synchronous way. And +1 means that the opposite. It's a positive relationship, that one goes up, the other one goes up in a perfect way. You rarely get -1 or 1, right? Perfect correlations, but you do get higher or lower ones. So 0.68 is a pretty high number, so they're pretty strongly correlated. Again, that's consistent with what we saw in the graph. But one of the things that we want to take into account of when we look at statistics like this, and this kind of goes back to our earlier discussion about confidence intervals, we're often interested in knowing to what extent this number is real, and to what kind of trust can we have it. Because we should always suspect that the data set that we're working with, which is almost invariably a sample data set, may not be representative of what's really going on. It may be kind of giving us spurious or uncharacteristic patterns. And so one way that we can check for that is to do what's called a t-test, or more often we look for what's called a probability value. And this p-value that we're going to look for is a separate statistic that tells us essentially what's the likelihood that we would be wrong to accept this number, or rather, to be very formal about it, to not reject it. So whenever we do statistics like this, they call them inferential statistics, which means you're making inferences. And when you make inferences from a statistical perspective, you're very interested in identifying where you might go wrong. And so the formal test for that is to look at a p-value, which again gives you the chances that you're wrong. So in order to calculate the p-value, we're going to need another number, which is just simply the number of the data points or data set, the size of our data set that we're working with. And that's nothing more than a count of the data that we've got going on here. So I'm just going to use the count function over here in the cases to count up how much data we've got that we're working with. So I'll just count the date column to give us a number. So count A2 to A121. So we've got 120 cases, 120 records, right? Data is 120 years of data. So that's what we need. Now the second part, this is where it gets a little complicated, where we calculate our p-value. Okay. Normally when you use advanced statistical software, which Excel is not, this is something that gets generated automatically whenever you ask for something like a correlation or a regression value, like a trend line. You're given the p-value to assess it. But in Excel, we kind of have to we have to do a little extra work, unfortunately. So this formula that we're going to put in is going to be a little ugly. So again, put on your seatbelts. Okay, here we go. So the formula that we're using starts off like all others. It starts with equals, and then we're looking for this formula called t-dist, T-D-I-S-T. Okay, it's basically for a student's t-distribution, which is a way of judging, the probability of something, particularly when you're doing a test to see whether or not something is true or not true. So the t-distribution inside of that is going to be wrapped into a other formula. So we're going to put in 2 parentheses right there. Okay. And the first thing that goes into that is going to be our correlation value that we just had there. And then we're going to multiply that by the square root, okay, oops, SQRT, right, square root of, and then we'll put in parentheses again, the number of cases minus 2, okay. And here, this part, this part of it is basically that number of cases minus 2 is what we call the degrees of freedom. It's a way of controlling the test to take into account how much data you're working with, essentially. So we'll take that, and then we'll divide that by the square root again, square root of 1 minus, and then we're taking basically the correlation value and squaring it, basically multiplying it times itself, close that parentheses, okay, and then we're going to add 2 more closing parentheses, put a comma there. You can see how it's guiding me in terms of what I should put in the formula. The next thing is the number of cases, okay, and then one last thing, how many tails. We're doing a 2-tail test, so we'll take 2, you can just type in 2, and then we can close off the parentheses right there. So you get that? So it's a long equation. So when you hit enter, right, you end up with a number, right? So what is this number? Okay, so this number is the p-value. So first of all, what is literally the number? Well, you see 5.24, and then it goes on and it has e minus 18. And what that means is that this is a very large, a lot of digits in this number, but the e minus 18 means you take that decimal point and you move it 18 spaces to the left. So what that would mean essentially is you have 17 zeros in front of that 5 if you were to write it out. But it's written in scientific format because otherwise it's too long of a number, it's hard to read. So this is just a shorthand. But what does it mean? Essentially, this is the probability that you would be wrong in rejecting the idea that there's no correlation, right? So this sounds kind of weird and backward, but when you're looking at an inferential statistic like this, like a correlation, right, you're trying to decide whether or not you should trust it. So the way that you do that is you set up a hypothesis test. And the hypothesis test has 2 components to it. You've got essentially a null hypothesis, and you've got the alternative hypothesis, okay? And the null hypothesis is the one that kind of you start off with. It says basically there's nothing going on, there's no correlation. And the alternative hypothesis is, this is going to sound even weirder, there's not nothing going on. So double negatives are allowed in statistics, apparently. So in any case, what you're trying to decide is whether you can reject the idea that there is no correlation, there's nothing happening here. And so what this tells you is the chances you'd be wrong to reject that. Okay, all right? And so by tradition, by convention, scientists use the 5% threshold. So if there's more than if it's 5% or greater chance that you could be wrong by rejecting the null hypothesis, you don't. All right. But if it's less than that, if it's less than 5% chance, then you can reject the null hypothesis and accept, well, nominally and provisionally accept that number. So all of that is to say is that this is well below 5%, right? This is, again, there's 17 zeros in front of that 5. So it's definitely a really low probability that you'd be wrong to think there's something actually happening here. So we can very safely reject the null hypothesis and provisionally accept the correlation to say, yep, that's probably what's happening. So there you go. There is clearly a correlation going on between death and damages. And again, as before, the question is, why is that the case and how is that the case?